Go ahead.
Hi, I'm the project lead for the Sun Studio Performance Analyzer, and I'm going to talk today about three projects: the Performance Analyzer, the Thread Analyzer, and D-Lite. Most of the engineers working on all of these three projects are present at the show, and so you can get demos of all of them there. So what I'm first going to talk about is the Performance Analyzer. New features in the previous release, the release that just came out, and where we're going in the future. Same thing for the Thread Analyzer, and then I'll talk about the D-Lite project, which is just starting. So in the Performance Analyzer in Studio 12, we have a couple of new features. Count data, which is available for Spark only. Hardware counter support for new chips, including the Fujitsu Spark 64, Niagara 2, the AMD Barcelona, and the Intel Core 2. And there's some other features which I won't have time to talk about, but there's a bunch of slides at the end of this. The slides will be posted, and there's a bunch of slides describing these other things like index objects, descendant process handling, attaching and collecting data, better control of the GUI, and clock-based data space profiling. Count data is invoked with collect -c on, and it uses a technology called BIT to do count instrumentation. It will compute function counts, instruction counts, and instructions annulled as metrics. They're exclusive only because of the way the instrumentation is done. We don't get call stacks. And it will work on the A.out and both statically and dynamically linked shared objects. There's no call or callee data or timeline data because the technology has quite a different basis. And there's also a new tab that shows instruction frequencies, and there's a report that matches it. You can also do collect -c static, which will produce data assuming that every instruction was executed exactly once. So here's what the count data looks like. You can see the metrics of performance that are up there for each function, just like for any other kind of data in the analyzer. Instruction frequencies is a report on how frequently each instruction in your executable was executed. And that's all I want to say about the last release. I normally give a 30 to 40-minute talk on only the Performance Analyzer. I'm now giving a 20-minute talk on three projects. So I'm talking really fast, but at no time will my hands ever leave my wrists. So for the future directions, the main thing we're concentrating on is improved NPI support. And we're doing two things with respect to NPI. We currently do NPI tracing, but we don't really deal with tying messages, sends and receives together. We want to do that. And we'll collect a lot more statistics on NPI usage, and you'll be able to see that data. And we're also working on another technology that captures state information from the NPI library. That is, whether NPI is doing work in NPI or is stalled for some reason in NPI. Stalled either because it's waiting for a message to come in or because it's waiting to get access to a resource. We're also going to do work in something we call analyzer personalities, which is a more graceful way of customizing what the analyzer looks like. It also will allow us to give different looks to the analyzer for different kinds of data, which is something we kind of do now. Although you may not know it, both the analyzer and the thread analyzer are fundamentally the same program. They're just customized slightly different. And we're going to generalize this so that if you have NPI data, it comes up in a different way that's more suited for analyzing NPI programs. And we're doing improved OpenMP support. We have a significant improvement in the data collection performance for OpenMP, and we expect to support OpenMP 3.0, including tasks management. As I said, all of these are research now, no product commitment. So anything I talk about in the future, you should know that we're working on it, but we're not committed to putting it in the product. So here's a quick view of the kinds of things we want to be able to display based on our NPI work. So we'll have arbitrary combinations of 1 and 2D displays to show you different kinds of data, scatter plots, and so forth. And there are actually also other NPI performance tools available. Some of them are already available on Solaris and, for that matter, Linux, JumpShot and Vampyre Trace. And there's a third-party version of Vampyre that's also already available on Solaris. Thread Analyzer is a new product that we introduced in the last release, which allows the user to explore data races and deadlocks in multi-threaded codes. In order to collect data for a data race, you do collect -r races. For deadlocks, it's collect -r deadlocks. And for races, you have to compile with a special flag that says you're instrumenting for data races. Once you've collected an experiment, just like you do with the performance analyzer, you can use either a new command called THA or the analyzer or ERPrint to look at the data. The THA command is actually the analyzer, but customized to show a display that's better suited for the thread analyzer types of work. Here's a screenshot of what it looks like for data races. What you can see is there's a list of races, and the races are all aggregated by common call stacks. So what you see here is that there's one access, which is a write access on line 50 of pthread_prime.c. The second access is also a write access on the same line, but in a different thread. And you see underneath it there's this total traces. Although we do the aggregation, you can, in fact, see individual examples of the races in your data. For deadlocks, there's a fairly similar display that shows which locks are being held and which locks are being requested from the different threads. And so you can see what's going on and whether or not there's a deadlock. Both the deadlocks and the data race will be displayable in the booth. That is, there will be people giving demos of that functionality in the booth at the show. And both of those use something called dual source, which is in the analyzer as well, which allows you, for example, in this case, you have a selected detail for a race. These are the two accesses in the race, and you bring up dual source, and you see the source line for each of those accesses. What we're doing in the next release, or what we're working on for the next release, are threading logic error detections, that is, collect -r pthreads, which will show you errors and how you're using your pthreads, and collect -r OpenMP, which will show you logic errors in using the OpenMP runtime. And we're working on GUI improvements. Among them, things that we want to be able to do, we want to be able to show you the variable names, that is, the names of a variable that is involved in a data race. We want to report both actual and potential data races. Currently, we'll only report data for data races that are encountered in the scheduling in that run. But one of the things about data races is that they sometimes show up and sometimes they don't. And whether they show up or not depends on how the system and the libraries schedule the various threads. We would like to be able to report a potential data race no matter how the threads would be scheduled. We're also adding support for OpenMP 3.0. And we'd like to be able to do data race detection for uninstrumented binaries. As I said earlier, in order to collect data race data, you have to compile with a special flag. We'd like to be able to not do that. We're also investigating data race and deadlock detection for Java programs. Probably not so much interest for HPC, despite many attempts to make Java interesting for HPC. And we want to do other improvements in the GUI to make it easier to navigate through the data. The objective of all of our tools is to be able to collect the data and show you a display and minimize how many times you have to click on the mouse to get to the point where you really understand what's wrong. So that's part of the work that we're doing for the thread analyzer. The last of the three topics I want to talk about is the D-Light project. And again, this is research. There's no product commitment to it yet, although there is an express release that does have D-Light in it available. D-Light is essentially the performance analyzer meeting DTrace. DTrace is functionality that was put into Solaris. It's an extremely powerful technology for understanding what's happening on the system level or the application level. And D-Light is a way of getting graphical user interface to make it easy to exploit that power. As I said, DTrace does dynamic tracing for both the kernel and user space. You can have user land statically defined tracing probes. These are called USDT probes. And in many of the virtual machines that are run on the system and runtime codes, we have DTrace probes compiled in. So that applies to Java, to Ruby, to PHP, Perl, Apache, Mozilla, Postgres, and many others. The intent was to provide stable observability and profiling interfaces into these applications. And we will use those interfaces and other interfaces to create what are called DTracelets. A DTracelet is an XML file that specifies a DTrace script, that is how to run DTrace on a particular application. And it also describes the data that's being collected so it can be more gracefully displayed. The user model for D-Lite is pretty simple. The first thing, you bring up a GUI. The first thing you do is specify a target. And then from a library of available DTracelets, you drag and drop the ones whose data you're interested in collecting. Click on the record button, and then that will start the process running and start recording data. And you can see a timeline-like display of each of the events as they come in. You can examine those events. You can save the data. You can look at a particular event and look at the call stack of that event and look at the source at the point of that event. Click on the stop button when you're finished with the experiment, and then you have the choice of either saving or discarding the data for future analysis. The design objectives of D-Lite were to make the technology very much developer-oriented. The emphasis is primarily on application developers, not the system developers. And we want to show the best information possible. We want to show native call stacks. If you're looking at Java, we would show Java call stacks as well. Source lines. And for post-mortem analysis, the model is you want to collect the data once and examine it many times, because until you've begun to look at the data that's being displayed, you really don't know how you want to aggregate the data, how you want to filter it and examine it. And the intent is to allow for both remote and distributed analysis of the data that's being collected. And we also will describe how an expert user could write their own DTracelets. That is, how they could customize DTrace scripts to get at what they want, describe them as a DTracelet in the XML file, and make those available so that their technologies can be shared with other users. Current status, we have a version that was working. It's available in Sun Studio Express in June 2007, and we expect it to be in future Express releases as well, and there's one coming up fairly shortly. Currently, the D-Lite is a plug-in to the Sun Studio graphical development environment. It has several DTracelets to collect data, a Java object monitor, a file I/O monitor, and a few others. And it shows, as I said, the timeline view for the data that's been collected. You can see native and Java call stacks and navigate to source for it. So I have raced through my talk in the interest of saving Ruud's life here and allowing the other speakers to talk. As I said, there are lots more slides with more information, which I'll go through in the manner of Andy Bethelsheim. And so that's all I have to say, and I'm happy to take any questions.
Thanks, Marty.
Oh, one more thing I wanted to say. If you can find Roman Shaposhnik, he will be able to do demos. That's him. He will do demos of D-Lite on his